Hello and welcome to the Unit 6 podcast on Chapter 14.1. I'm Mr. Sakaguchi.
And I am Mr. Lin.
Today we'll be talking about some of the gas laws. As a brief review, remember that these gas laws are based upon assumptions made with the kinetic theory. I'm not going to read all these again, but you kind of get the general gist of this. Remember again, actual gases don't obey all of the postulates of the kinetic theory, but most of them do under the
Ideal
correct
circumstances,
conditions. Under the correct conditions.
Right.
Things that affect whether or not something behaves ideally or real is based upon number of particles, temperature, pressure, and volume. And these factors are what we're going to be examining as part of gas laws. One of the first laws that we'll talk about is Boyle's law. Boyle's law basically is the idea that pressure varies inversely with volume if we keep temperature and the amount of gas constant.
So if you squeeze a container, an airtight container, and as you squeeze it, you're going to feel the container push back more and more at you because the pressure is increasing. So what you're doing when you're squeezing the container is you're making it smaller. You're decreasing the volume, and as a result, the pressure gets larger. Then when you let go, you let the volume increase, you'll feel that the pressure is less. And that's all Boyle's is talking about, but he was able to apply an equation to it and make it calculable.
Now remember, when we're talking about these situations, if I decrease the volume, that's less space for the gas particles to move around, so they collide with the ends of the container more frequently and a lot of times with greater force, hence the pressure increase. If I increase the volume, more space, less collisions, less force, so a drop in pressure. We also have Charles's law. Basically, the idea here is we have a direct correlation between volume and temperature, assuming pressure and the amount of gas is constant, where V1 over T1 equals V2 over T2. One important thing to note is that your temperatures in gas laws always need to be in kelvins, and to convert to kelvins, remember you take the degrees Celsius and you add 273 to it.
Right. So all that's just saying is that as things heat up, the gas is going to want to take up more space because the gas particles are moving faster. If they're moving faster, they're going to push against the containers more, and if this will cause it to expand and take up more volume. Again, for all of your gas law equations that involve temperature, you need to have it in kelvins. So a lot of times you will be given a problem in degrees Celsius because that's how most of the world works, but you have to convert to kelvins because that's how the gases actually work with.
And if you think about it from a mathematical point of view, you can't divide by 0, and notice how temperature is in the denominator. And also if we use the Celsius scale, it has negative values, which means you'd end up with negative volumes, which isn't possible either.
Right.
We also have Gay-Lussac's law. Gay-Lussac's law basically says that we have a directly proportional relationship between pressure and temperature if volume and the amount of gas is constant.
So basically what that means is as temperature increases, the pressure will increase as well together with it, and oppositely as well. As the temperature drops, pressure drops. And you see this in the figure to the right with the balloon. As the temperature got higher, the balloon expands because the pressure inside the balloon got higher as well. And then when temperature dropped, the balloon collapses. And you can do this yourself. You can actually take a balloon, blow it up, stick it in your freezer, and you give it like half an hour to an hour, and you'll come out with it shriveled.
Also, remember, as with Charles' law, the temperatures need to be in kelvins, not in degrees Celsius. That's it.